Нормально. Порядок конструирования.
So good morning. Today we have Sanja Konjik, who will give a talk about fractional modeling of various problems in mechanics.
Thank you very much. Okay, so I'm from University of Novi, from Serbia. Well, some of you already know, I bet. Okay, thank you. So I will give several talks, so 3 talks, today 2 and on Monday the 3rd one, about fractional modeling of various problems in mechanics. So we will use fractional calculus in modeling wave propagation in viscoelastic media. And for that reason, at the very beginning, I will just briefly introduce basic notions and results from fractional calculus. I realized that you learned about fractional calculus in previous days. So from Virginia at least, and I don't know who else.
Professor Lechko.
Okay. So probably most of the things will be just repetition for you, but that's always good to repeat things before we go into details. So let me start just with this first slide is kind of historical one. Although we are not familiar with fractional calculus during our regular education in primary, secondary school, or even at faculty. So, in fact, fractional calculus is as old as the classical one, and I'm sure you learned that. So, origins of fractional calculus go back to the end of 17th century, and discussion between L'Hopital and Leibniz. They raised the question: could we differentiate with the order which is not an integer? And well, the first meaning of such derivative was given by Euler in 1738. But let's say that kind of solid foundation of the theory was provided with Liouville. That was the beginning of 19th century, so first half of 19th century. He gave a solid foundation of the theory, which is more or less nowadays still in use. And also a bit later, so it was 1847, but the paper was published quite later, so 29 years later. Riemann proposed the definition of a fractional integration, which we will see in a few slides. So since then, we have basic notions from fractional calculus, but still the real expansion of the theory and applications happened just maybe 30-40 years ago. So nowadays you can find applications of fractional calculus in many various fields, and that is why it is quite attractive, and nowadays many people do research in that field. And once we introduce definitions of fractional derivatives, we will also see why such derivatives are sometimes better than the integer order ones, or the classical ones. Okay, so in the theory of fractional calculus, special functions play a very important role, and I will just briefly go through the ones which will from time to time meet on these slides. So first is the Euler gamma function, defined via this integral. As you can see, I somehow believe that you are familiar with this definition. It is a kind of generalization of the factorial function, and it already appears in the definition of fractional integrals and derivatives. Then we also need the beta function, it is two-parameter function. And in this last relation, you can see also connection between beta and gamma function. In one moment, we will use it to calculate some fractional derivatives. And also, the Mittag-Leffler functions, we have two types, one parameter Mittag-Leffler function and two parameters, so this E alpha and E alpha beta. Mittag-Leffler functions are in fact generalizations of the exponential function. So you can see that, for example, from this third special case, why they are so important for fractional calculus. Here I try to make just the basic examples of differential equations, so ordinary differential equation and fractional differential equations. So if you have a first derivative, so this type of equation, its solution, so with the initial condition, its solution is given through this exponential function, e to the at. But if you replace first derivative with a Kaputa fractional derivative, we will introduce it very soon, with the same initial condition, then the solution, one can show that the solution is then given in this form. So this exponential function is replaced in a sense by this Mittag-Leffler function. So it takes the role of this exponential function from the previous case. And if you go to the Riemann-Liouville fractional derivative, you have to change a bit your initial condition. Then again, you have a solution which is given through the Mittag-Leffler function. So those Mittag-Leffler functions are really important when solving fractional differential equations, and as you will see also in our examples, we will use them. They will appear in our solutions. Of course, these are some just very basic examples. Okay. And when we start to talk about fractional calculus, typically we start with fractional integrals. So first we introduce fractional integrals. And for L1 function and alpha positive, we define the left Riemann-Liouville fractional integral of order alpha and the right one. So where I put here. Okay, so we introduce first the left Riemann-Liouville fractional integral. This is the notation which we will use for integration, fractional integration. So it is 1 over gamma of alpha. You see immediately the special function here. And then integral from a to t minus theta to alpha minus 1, u of theta d theta. It is called left because in this integral it collects all points on the left-hand side of your point at which you want to calculate your fractional integral. So it is from a to t. And then the right Riemann-Liouville fractional integral of order alpha, well, similarly defined, but then you have from t to b, and then a little bit changed this integrand here. So it is defined for arbitrary alpha positive. So later we will see with going with alpha negative, we go into differentiation. Fractional integration has some nice properties. First of all, in the case when alpha is just a natural number, it is n-fold integral of u, and it can be easily calculated and checked. So this is this first relation. And what is also important here, that fractional integration has this semi-group property. So if you integrate with respect to order alpha, first beta and then alpha, this is the same as you change the order of integration, and this is in fact the integral of order alpha plus beta. Well, one more thing, this formula will be important later. So if we want to calculate what will be the fractional integral of, for example, power function, here t minus a to some power mu, then, well, you insert that into the definition, calculate, and at the end you obtain an expression of this form. So it is this quotient of these gamma functions, and then t minus a to the power mu plus alpha. That will give later on an important property of fractional differentiation. Okay. And then we go to differentiation. So for absolutely continuous function, u, and first we start with alpha, which is between 0 and 1. So 0 is included, 1 not, so strictly less. We define the left Riemann-Liouville fractional derivative and the right Riemann-Liouville fractional derivative. So the left one is in fact the first derivative of the integral of order 1 minus alpha. And if you write that out completely, then you obtain 1 over gamma of 1 minus alpha, derivative of the integral from a to t, u of theta, t minus theta to the power alpha, d theta. And in a similar way, you go to the opposite side, to the right side, but here you take minus first derivative of the corresponding integral. So somehow immediately we notice that since we call it Riemann-Liouville fractional derivative, somehow it is to be expected that we have also some other types, and yes, that is true. There are many different types of fractional derivatives. We will learn one more and use one more, that is Kaputa one, but these two are of course not the only one, there are many more. There are also some discrete versions of fractional derivatives, like the Grunwald-Legnicko, which is, for example, more useful if you want to do some numerical analysis. And okay, here we stop before 1. 0 is included. If you really put alpha equals 0 into this definition, you obtain that the zero derivative is in fact it is the function itself. And also one can show that if you let alpha to tends to 1 from the, which is at the left hand side, then in the limit you will obtain the first derivative, meaning that this notion of fractional derivatives generalize the integer order derivatives, so at least for 0 and 1. Okay, so here because typically we talk about fractional derivatives and work with them more or less theoretically, but rarely we calculate fractional derivatives. And here is complete calculation of the fractional derivative, Riemann-Liouville, left one, of this power function, t minus a to the power minus mu. So at the end you obtain an expression like this, but you can maybe just see that what we do in between. So it is maybe not so straightforward like with integer order derivatives. And why is this example important? Because it tells you that there is one property of fractional derivative, at least this one, Riemann-Liouville type, which is different from properties that integer order derivatives have, and that is that if you take a constant function, its fractional derivative is not 0. But the role of the constant function for the Riemann-Leibniz fractional derivative is played with by this function, so the power function, t minus a to the power alpha minus 1, which can be seen from this calculation above. That is an interesting property, of course, which influences many other things when you work with fractional derivatives. And as I mentioned, we stopped there when defining fractional derivatives. We stopped at 1, but of course we can prolong this formula and define a fractional derivative of arbitrary real order. So we do that as going always in these one-step intervals. So if you take alpha between n minus 1 and n is integer, then you have this definition of the left Riemann-Leibniz fractional integral and the corresponding right one. So it is 1 over gamma n minus alpha, before it was 1 minus alpha. Then you differentiate n times this integral here. In our models, we will typically use fractional derivatives of order between 0 and 1, so the previous definition will be always in use, but of course you can go. It of course depends what you want to model, which phenomena, and that somehow tells you which type or which order of derivative to choose. Some properties. So if you first integrate take a fractional integral for the alpha function u, and then fractional derivative of the same order, you will come back to the function. That is the same property as for integer order derivatives and integrals. But in opposite order, it is not true. In fact, you have this relation here. So here I try somehow to point out some differences comparing to classical integer order derivatives and integrals. And also, so few slides before, we saw that for fractional integrals, we have that semi-group property, so we can really change the order of fractional integrals without any restriction. But here, for fractional derivatives, that is not possible in general. And we have one example or counterexample which shows us that it is not the same. So here the function is t to the power 1/2, and so we start from point 0, a0, and differentiate with respect to 1/2 and 3/2. And then if you calculate first fractional derivative for the 0.5 of this function, we will obtain gamma of 3/2, which is 1/2 square root of pi. And as we saw in the previous slide, the fractional derivative of order beta of this function is 0. So, if you take first fractional derivative for the beta and then order alpha, you will get 0. And if you exchange their order, you will get minus 1/4 t to the minus 3/2. So here, in general, we cannot arbitrarily choose the order of differentiation, but also we don't have this semi-group property, so it is not a derivative of the order alpha plus beta. And one has to take that into account when dealing with fractional derivatives. Okay, and as I showed you on one example, so calculating fractional derivatives of just arbitrary function is not really always easy, and there are a lot of computations. And here is just the table with some fractional derivatives, so you can see expressions which you obtain and on this left-hand side, you see that we just choose some, let's say, typical functions, so constant, power function, exponential function, and so on. And when you calculate their fractional derivatives, you obtain this type of expressions. So even that first step is somehow not very pleasant to deal with. Already several times I mentioned that besides Riemann-Liouville type, there is also the so-called Kaputa fractional derivative, which we also use very often in our work. And it is defined in the following way. So again, for absolutely continuous function, here definition is immediately for arbitrary alpha, so between n-1 and n. We will use this additional letter C to indicate this Kaputa type. And then you have 1 over gamma of n minus alpha. And that, if you now recall, in the definition of the Riemann-Liouville fractional derivative, we had in front of the integral the derivative of order n, so d over dt to the power n. And this derivative, which was in front of the integral, came into the integral directly to the function. So in the definition of the Kaputa fractional derivative, now you have integral from a to t, and then you take as derivative of function u divided by t minus theta to the alpha minus n plus 1 and integrate that. And the corresponding right version. So the basic difference is that the differentiation which we had in front of the integral with the Riemann-Liouville case came into the integral, but still we can relate these two definitions. And okay, say here, so the left Riemann-Liouville fractional derivative is equal to the Kaputa one, and then you have this additional term. It is sum. Here you have some powers of t and the gamma function, and then derivatives of your function u calculated at the initial point, so a, and up toward the k. So it depends, of course, which order of derivative you're considering. Here is the general case, alpha is between n minus 1 and n, so it takes all first n minus 1 derivatives of function u at the initial point. Of course, from this formula, we can immediately conclude that if we have zero initial conditions, then these two types of derivatives, so Riemann-Liouville and Kaputa, coincide. So if this condition is satisfied. And contrary to the Riemann-Liouville case, for Kaputa fractional derivative, we have a property that derivative of the constant function is zero. That is property which we have for integer order derivatives, and in some situations it is important to preserve it, to have it. For example, when you think about, when you consider I don't know, fractional symmetries, fractional variational problems, and then fractional conserved quantities. So then the question would be what conserved quantity in that case, in the fractional situation, would be. So if you don't have this property. But that is a different story. Okay, some identities interesting for these fractional derivatives. Okay, we have linearity. We don't have Leibniz rule. But there are some versions of the Leibniz rule. Well, some expressions that, let's say, replace this classical one, Leibniz rule. Here you can see one possibility to express what the fractional derivative of the product of two functions is, but here you need analytic functions, and you use then just all integer order derivatives of both functions. Well, of function v, and here fractional derivatives of function u. So let me say it is, from the theoretical point of view, it is a nice formula, but from practical point of view, not really very useful. And also here you have a representation of the fractional derivative of function u with respect to all integer order derivatives. But here again you need analytic functions, so somehow more than you need for the definition of fractional derivative. So because you need in this formula all these derivatives to exist. And also, this is interesting formula, that is fractional integration by parts. So if you compare it to the integer version, which we, of course, we all know and use often, it is kind of similar. So the derivative goes from one function to another, but here the left derivatives, which was on the function g, goes to this function f as the right fractional derivative. So this other version. And also you don't have that, you remember that in the classical integration by parts formula, we have that additional term, which is a product of these two functions, but evaluated at those boundary points. And in fractional version, we don't have that. And this is, for example, very important when we study the fractional variational calculus, because for deriving Euler-Lagrange equations, we all the time need to apply it. Okay, and since most of the time we will be dealing with fractional derivatives, but in a distributional setting, then it is important to introduce these notions also in this sense. In our work, we will use different spaces of distribution. So D prime, S prime. When we use this plus notation additionally, it means that our distributions are supported at a positive half line from 0 to infinity. And that is because most of the time it will be related to a variable t, time variable, which starts from 0 and goes. And okay, in the distributional setting, we consider such family of functions, so f alpha. It is a power function, t to the power alpha minus 1 divided by gamma of alpha, and then cut by Heaviside function, h, for alpha positive. Or if alpha is negative, then you choose arbitrary integer such that n plus alpha is positive, and then you take f alpha plus n, so this is the first type, and differentiate n times. And here I wrote down several first members of this family. So f1 is just Heaviside, f2 is t supported only on a positive half line, f3 is t squared over half, and so on. And if you go in negative direction, f0 is delta, and then derivatives of delta. And then when you see how these distributions look like, then you can immediately see that if you make convolution f alpha with your function from s prime plus, then and alpha is greater or equal 0, then you obtain fractional integration. And if alpha is less than 0, then you obtain definition of fractional differentiation. One more type of derivatives, which we will also later use, that is distributed order fractional derivative. This is formal definition of this derivative in the spaces of distributions. But let me point out that look here, this first integral here, what you do, you take fractional derivatives of function u, and somehow go through all orders of alpha in some interval you want to consider. So this is support of phi. Phi is a function of alpha. This is a kind of weight function. So you somehow collect all fractional derivatives of u in some interval. And that is a distributed order fractional derivative. And we will see how it appears in our model somehow also very naturally. Since we will be dealing with generalizations, fractional generalizations of the wave equation, the basic tools for solving such problems will be Fourier and Laplace transforms. And I here just repeat definitions. I believe you're all familiar with them. So those are classical definitions of Fourier transform, Laplace transform, and some properties which will be important for us. So we know how Fourier transform acts on the derivative of function, but let's say the same formula remains true if you replace integer order derivative of function with fractional derivative. So you have here I omega to the power alpha. In integer order case, you have just, in fact, instead of alpha, you have that integer, the order of derivative here. And the same for the Laplace transformation. Also, we have here a Laplace transformation of the distributed order fractional derivative. Okay, it is a Laplace transform of u, and then here you have phi of alpha applied to s to the power alpha. And of course, those are classical properties of Laplace transform, which we'll often use because we will have convolution and also from time to time apply to Dirac delta. I think that I have also here some. Okay, so when we start with our equations, so we will typically apply Laplace transform, go in Laplace domain, solve everything, and then have to go back. So we will typically first obtain a Laplace transform of our solution, and the question would be how to obtain solution. And then we will, from time to time, obtain in the Laplace domain functions of this type. So here I just extract, even we use this table to see, so not to calculate every time everything, but if you recognize a function of any of this type, then you can immediately know what the original function is. And you can also notice here on the right hand side that some special functions, and most of the time this Mitter-Lafleur function appear, and that is how it will also appear in our solutions, as I mentioned at the beginning. So from time to time we will use this table for our calculation. And so far we have talked only about fractional derivatives of real order, but in fact we can go even further, so extend the notion of fractional derivative also to complex numbers, so the orders of fractional derivatives can be complex numbers. And if so we have eta, a complex number, with real part between 0 and 1, strictly greater than 0. Later on we will analyze the other possibility. This less than 1 is just this first possibility when the order of derivative is between 0 and 1. and of course you can prolong the definition for, in fact here you can have whatever you like, then in fact you can preserve the definition. So completely the same definition can be applied to complex order of differentiation and absolutely continuous function. And in the case that eta is purely imaginary, so you don't have real part, then the definition of fractional derivative is given by this formula here. And also in this case, we have the same properties for the Laplace and Fourier transform. When applied to fractional derivatives of complex order, you obtain s to the eta or I omega to the eta, and then Laplace or Fourier transform of your function. Okay. I think that was introduction of fractional derivatives and some properties in fractional calculus, which will be important for our work. So now we go to our first model. That would be a fractional Zener wave equation. And okay, here you can see immediately the equation which we would like to solve. So it is of second partial derivative of function u with respect to t. So u depends on x and t. X is one-dimensional spatial coordinate, t is time. Here you have operator L that acts on the second partial derivative with respect to x of function u. And this operator L from this equation is in fact convolution operator of the form, so it is inverse Laplace transform of 1 plus s to the power alpha over 1 plus tau s to the power alpha. Alpha is considered here to be between 0 and 1. This parameter tau is also between 0 and 1. And although just looking at this equation, one can immediately ask why to solve it, how we obtain it, why in that form. I will explain that immediately. But what we want to do first to derive this equation, so to see how we obtain it, what does it model, to analyze it, and then to solve it. So this will be our generalization of the wave equation. Of course, you immediately see that if you just cancel this L and insert constant C, you obtain the classical wave equation. Maybe the natural guess would be that if you want to go to a fractional domain with a wave equation, you can simply replace some of these derivatives, integer order, with fractional ones. So instead of second order derivative, you take derivative of order alpha between 1 and 2. That would be a possibility. But why don't we do that? Because in fact the classical wave equation is derived from three basic equations of elasticity. Those are this first one, which is a consequence of the second Newton law, equation of motion. Then you have this second equation. This is constitutive equation. Here it is written, it is Hooke's law. And then the third one is called the strain measure. So this is system of three equations, and you have three unknown functions: u, that is displacement, sigma, stress, and epsilon strain. C is a constant. All three functions depend on two variables, x and t. So x is spatial variable, as I said, so we will consider one-dimensional case concerning space variable, and t is time. And if you insert epsilon from this third equation into the second one, and then sigma from the second one into the first one, you will obtain the classical wave equation. And so, since each of these equations is some physical law and explains you what's happening, how to say, behind the scene. For example, this second equation, Hooke's law here, constitutive equations, tells you that sigma, stress, is proportional to strain. And this equation holds for elastic media. So if you have elastic body, this is the law which relates stress and strain. If you want to consider wave propagation in fluids, then you have to replace this Hooke's law with Newton's law, which relates sigma and epsilon. So sigma would be proportional to the first derivative of epsilon. And then again you derive the corresponding wave equation. So that first idea, which I mentioned on the previous slide, to just replace arbitrarily any derivative, integer order derivative with fractional ones, is, how to say, from the mathematical point of view, it's okay, you replace and you solve problems, they're always interesting. But from the physical point of view, you somehow want to have explanation or reason why you do something and to preserve all laws that hold. So here, we want to study wave propagation in viscoelastic media. So that is materials which possess both viscose and elastic properties. And that is how fractional derivatives somehow naturally come into this story. So elastic case is relation between sigma and epsilon through zero derivative, and for fluids or viscose materials it is through first derivative. So somehow one can expect that for viscoelastic materials the relation between sigma and epsilon would be through some derivative of order alpha, which is between 0 and 1. And with that order of derivative you can in fact order, and also this constant here which will appear, you can more precisely describe the media in which you consider wave propagation. So if the media possess more, let's say, elastic properties, you will go with the order of fractional derivative which is closer to 0, because that is closer to the elastic case and to the Hooke's law, or on the opposite side, go to orders of derivative that are closer to 1, if you go to media which is more viscose. Okay. Oh, yes. So this I already said. How we so we want here to preserve the first and the third equation. So because they should remain unchanged in any type of media, and just play around with this second one, with the constitutive equation. Although there are also reasons why one can generalize also this third equation. That was also done by my colleagues, Ljubica Prnica and Dušan Zorica, but I will not speak about those cases. Even in the classical case, if one wants to study viscoelastic materials and wave propagation in viscoelastic body, then Hooke's law is replaced by a so-called Zener model. In Zener model, you combine on both sides, on the stress and the strain side, it is a linear combination of the zeros and the first derivative. That is how we model viscoelastic bodies without use of fractional derivatives. These constants here that appear, A and B, they are typically experimentally determined. Of course, they depends on the media in which you consider wave propagation. But it turned out that it must hold that both are positive and A is strictly less than B. So that is always confirmed experimentally, but also it follows from the second law of thermodynamics. And then we will generalize that. So here that, as I said, the property of the media was somehow incorporated here in constants A and B. But one step further would be also to replace these first derivatives with fractional ones, so that you can even more precisely describe your material, now with constants A and B, and also with the order of fractional derivative. As I said, you can now, with this alpha, you can balance more between elastic and viscous case. Then you can go even further and say, okay, why just take, so you see here we take the zero derivative of stress and strain and then add some fractional derivative of stress and strain, but why not adding some more fractional derivatives? And that is how we obtain this linear model. So it is just a linear combination of arbitrary numbers of fractional derivatives of stress and strain. So the question here is, what should be restrictions on these parameters in the equation, so on these constants, A's and B's, and also on these orders of fractional derivatives, alphas and betas. And we will discuss that later. So it is not just arbitrary relation, so take whatever you like here, but there are some restrictions. And the next step would be, okay, here you have just arbitrary sum of fractional derivatives, but if you take more and more, in the limiting process, you just collect all of them between 0 and 1, and that is how you arrive to Cauchy relation, which involves distributed order fractional derivatives, which we introduced. And so, if you want to describe viscoelastic effects, you will choose your alpha between 0 and 1, alpha or alphas, whatever, depends which model you take, or for viscoinertial effects, alpha should be between 1 and 2. We will consider this first case. Okay, so let's go back to our problem. We start from this system of three equations. As I said, the first one is the equation of motion. Now for the second one, for the constitutive equation, we choose the fractional Zener model. So it is sigma plus tau alpha derivative of sigma equals epsilon plus alpha derivative of epsilon. And the third equation is strain measure. So it is one-dimensional case. So you can imagine that we have, I don't know, let's say some rope or wire or something like that. It is time variable. For this constant tau, we suppose that it is between 0 and 1. As I said, for the order of fractional derivative, we will take to be between 0 and 1. We use here Riemann-Liouville operator, and okay, I explained how we call these equations. So if we go a bit back to the equation I started from, this one. So the question is how we can obtain this type of wave equation from this system which we now introduced. And that is not difficult. Okay, so in order to solve problem, we need to suppose some initial and boundary conditions. We will assume to have initial displacement. So at the initial moment 0, some initial displacement u0, initial velocity, B0, no initial stress, no initial strain. And from boundary conditions, we see that here we have, so x tends to plus minus infinity, so we can think of a long wire without ends on both sides. And then we assume that as we go further from let's say, starting from 0 at infinity, displacement vanishes and also stress. No displacement, no stress at infinity. So how to derive our fractional Zener wave equation? We will apply first Laplace transform to the second equation. If you do so, you will obtain here 1 plus tau to s to the power alpha, sigma tilde, so Laplace transform of sigma, and here 1 plus s to the power alpha, epsilon tilde. Then, so what do you need? You need here epsilon. Then you you will insert epsilon. So let me just see. So you, of course, you can express here either Laplace transform of sigma or epsilon. So we need sigma. So sigma tilde would be this 1 plus s to the alpha divided by this term here times epsilon tilde. But then you do apply the inverse Laplace transform. Check that this is well-defined element in the space of temporal distributions, and then sigma would be, so the inverse Laplace transform of this expression in convolution with respect to t with strain. And then insert strain from the third equation here, and then sigma into the first equation to obtain the fractional Zener wave equation, the expression which we had on the first slide. So the Cauchy problem, which we will be considering for our fractional Zener wave equation, will be, the equation now is given by this expression here. So this operator L is the convolution operator, exactly L is this part here. And we have initial conditions. Boundary conditions are automatically included in the space, into the space of temporal distributions. And in fact, in the space of distributions, this problem is equivalent to the following one. So here we introduce operator P. It will be of the form, so it is a partial derivative of the second order with respect to t of u minus our operator L acting on partial derivative with respect of the order 2 with respect to x of u, and then equals here you have your initial conditions. As I said, boundary conditions are already included into this space of temporal distributions, and what we know from the classical theory is that if we can find a fundamental solution to this operator P, so that would be a solution to the equation P times U equals delta, then we know that we have a unique solution to our problem, which is given in the form that fundamental solution S in convolution with respect to x and t with initial conditions, as written here. So what we want to do first is to solve this equation, or in other words, to find the fundamental solution to the operator P. So how to do that? We will apply the Laplace transform to our equation. So here is our equation, this one. So apply Laplace transform. Why what we obtain by applying Laplace transform. As always, such transform will convert your differential equation into algebraic one. So Laplace transform here with respect to the time variable. So after doing that, we will obtain, in fact, ordinary differential equation of the second order with respect to x variable. So this is the expression. This is really easy calculation. And so the question is, can we solve it? And if yes, we will obtain solution u tilde. So it will be Laplace transform of our solution. And then the second question is, can we apply inverse Laplace transform and obtain really a solution? And here we need one lemma to help us. So if we consider ordinary differential equation of the second order of the type, so the second derivative of v minus omega v equals minus f, where we assume that, so omega is a complex number, but just not on the negative real line. Then the solution of such equation is given as this convolution here and is element of S prime. And if you see why we need such lemma, because our equation here is exactly of that form. So our omega is this expression here, and our minus f is this on the right hand side. So in order to apply it to our equation, we need to check these two things. So first that this omega does not fall on the negative real line. And of course to check that this expression here is element of S prime. And those are quite some calculations. And of course one can check it. Once you do that, you then obtain solution to your equation. So u tilde, in our case, will be of this form here, this convolution here. Okay, I have that written here. And just rewriting this in the form, like in this second line, you see that we wanted fundamental solution, and yes, we obtain it, well, not really fundamental solution, but it's Laplace transform. So the next question is how to find the inverse Laplace transform of this expression here. And okay, first to check whether such expression has inverse Laplace transform, we use this theorem of isomorphism. We check all conditions and conclude that it can be, so we can calculate inverse Laplace transform, and S is in that case well-defined element of S prime. Also we know this relation. For such S, which we know that it exists, we know that the solution is then given by convolution of the fundamental solution with initial conditions. So the only thing that remains is to calculate the inverse Laplace transform. So from theory we know it exists, but how to calculate it? And here, and as well as in many other problems which we were solving, those are, well, a lot of calculations. I will just present several things. So here, I should make a break.
Good time for a break.
Maybe just finish this slide. Although it is long, I will be short. Okay. We use the Cauchy integral formula. We choose contour, which is appropriate for this problem. Here are all details, and I will not go into them. So along each of them, you calculate this expression here, and at the end, after calculation, you obtain your solution. So you obtain S explicitly, as given here, and solution to our fractional Zener wave equation as the convolution of this fundamental solution with initial conditions. Moreover, it is element of S prime and has support in the cone d over the square root of dou. Okay, break.
Thank you. Any questions or comments?
After next lecture.
After the next lecture, yes.
Okay.
Yes.
Quite hard, I know.
When you apply the Laplace transform to the differential equation who has both Riemann-Liouville integrals, you omitted the initial condition of the fractional integral because it's zero, so you are assuming continuity of the function, right? Because you didn't put any initial condition with the fraction Riemann-Liouville integral, right?
Kaputa. What do you mean?
No, here, well, oh, yes, yeah, one thing I forgot to tell you. Once we introduce or consider fractional derivatives in the distributional setting, like those convolution operators, then Riemann-Liouville and Kaputa are the same, they coincide, so in the distributional setting. In this problem, we are in the distributional setting, we deal with Riemann-Liouville fractional derivative, it is written, and when you apply Laplace transform, you just use the formula I showed you, and the initial conditions you have in your Cauchy problem. And as I said, boundary conditions are already included into the space of, into S prime.
Any other? Okay, thank you then again. And, in 11 minutes, feedback.